Multivariable calculus. We're looking at lesson 13.2, part 2. We're finishing up example 2 here and drawing the vector 1 comma 1/3. You can see that means go right 1, go up 1/3. That's this red arrow that we have right here. That would draw this blue point right over here. It's a point on the curve. It's a point that could correspond to this vector where the head of the vector is that point on the curve. Likewise, if we were to draw a tangent vector, go to that point of contact. Go to that specific point of contact. And I'm going to, again, maybe change to red here so that we can see this. From this point, 1 comma 1/3, we're going to go right 1/2, but then we're going to go down about 2/3. That's -2 over e. So here's down 1/3, here's down another. So this right here would be our r prime of 1. And that's our tangent vector. That's showing the direction of motion. And of course, that length right there is not guaranteed to be a 1. Very quickly, let's take a look at example 3. And it says, find the parametric equations for a tangent line to the helix with parametric equations. So here's the thing, guys. As we're looking at a line, we remember from last unit, last chapter, that parametrically we could define a line if we had a point, on that line. By the way, we do. Here's our x naught, y naught, z naught. But then we need a direction vector. Here's A, B, C is the direction vector. You'd think, well, what is the direction vector? Well, guys, the direction vector is r prime. It is, plain and simply, what we get with dx dt. Dx dt, derivative of 2 cosine of t, that's going to be -2 sine t. Derivative of y here, dy dt, that's just cosine of t. And the derivative of t itself is just a 1. And, right now, as we're looking at this, we can think, now, wait a minute. This direction vector, we have to plug in a particular t value. And here's something that we have to very much be on guard for. And it's going to show up so very, very much. What we need to be aware of, guys, is that here our t naught is going to be pi over 2. You're told that z happens to be a t. If you're beginning z naught, if this is going to be a point, the point of tangency, that's where we're going to be taking our derivative. So really what we've got here is our r prime of pi over 2. That's going to be, well, plug this in. It's going to be -2 sine of pi over 2. It's going to be the cosine, not just of t now. Now we know what t we're plugging in. It's pi over 2. And our dz dt, pardon me, I didn't write that down right. I took the derivative right. Certainly didn't write it as a differential nicely. That you plug in a pi over 2, you still get a 1. But guys, this is going to be sine of pi over 2 is just a 1. Cosine of pi over 2 is 0. And please understand, that's the direction vector of your line. R prime is always the direction vector of your line. So what are we seeing? X is going to be, well, what's your x naught? It's 0. What's your a? Well, that's -2t. How about your y here? Well, your y naught is 1. And you're actually going to have a 0 here. That's 0t. Your z is going to be your z naught, which is pi over 2, plus a 1t. So we could even clean that up a little bit more. We could say x is equal to -2t. Y is always going to be a 1. It's not going to change. and z is pi over 2 plus t. And that would be the equation of that tangent line written parametrically. Okay, so as we continue, just a few basic principles that are super important. If you have a constant out in front of a vector function, you can slide that constant out as you're taking a derivative. If you're adding two vector functions, if you take their derivative, well, it's just like taking the derivative of the one function, adding or subtracting the derivative of the other. Dot product. Ooh, this is important. Look, you've got u dot v. And what do? It's looking just like a product rule. We could say take the derivative of our first vector function, dot producted with the second vector function, plus the original vector function, dot producted with the derivative of the second vector function. And of course, these can be switched. You can change those orders around. Cross product, well, it's exactly the same. It's just like a product rule. You can see first we could take a derivative of that first vector function, but the multiplication that connects is a cross product. It's still a cross product of v arrow here of this vector v. Plus, now we take the original vector u cross producted with the dv dt. This chain rule, wow, this can look so funny once again. You got that bold U there. That bold U, I do want to say, as I said on the previous video, it's really shorthand for an arrow. You'll see that written in textbooks. So what if you have a vector function, but you substitute in another function instead of having t? Well, you'd say, wow, that looks just like the chain rule. Thank goodness it behaves just like the chain rule. You take the derivative of the outside, that's what we have right here, u prime f of t, multiplied by the derivative of the inside. And then finally, this one can look rather strange to kids here. They might say, wow, what is this f of t and the u of t? It can look so strange. F of t is not a vector, it's just a function. So we don't have a cross product or a dot product. And of course, we're just multiplying that to a vector function. And then we're going to take a derivative. Sometimes kids will say, I don't get it. I don't even see how that would be possible. Well, let's say you've got a vector function. And I don't know, let's just say the vector function is natural log of t, t cubed. And we'd say the sine of t right in here. Well, what if you had another function out in front and it was e to the t? Here's your vector function right here. That's u, right? And here's just some other function out in front. You can think, well, how in the world could we do that? Well, what this is saying is you could still treat it like you see a product rule. You can see more or less that you could have the derivative of the outside here, f prime of t times the vector function, and then plus f of t, now multiply that by the derivative of your vector function. So the first part of your product rule, you're taking the derivative of just the function, and then the second one, you're taking the derivative of the vector function. So basic properties important to remember. For this next theorem, this is so very, 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 very important to know that this caveat, the warning is, we are assuming that our vector r has constant length. It's got constant length. It's not going to get longer or shorter. And the length of it is just some number c. That's what we've got right here. So the derivative of a vector of a constant length, not a constant vector. The minute hand of a clock would be a great example of that. The minute hand of a clock, it might have the same length, but it's constantly changing the direction that it's pointing. If I said we've got a constant vector, however, that means that we're not changing direction either. This is just a vector of constant length. it can change direction. So let's just remember from chapter 12 that if you dot product a vector to itself, you're actually going to get the length of that vector squared. It's hopefully not too difficult. You can even look that up if you need to. In other words, what we're seeing is r prime dot r prime. If I'm calling that c right here, we'd get c squared. But now I'm going to take a derivative. And doing the derivative, you can see more or less I'm using this dot product rule right here. I'm going to say, look, I'm going to have, following this exact example, we could have r prime of, well, we'll just write it shorthand, is r prime dotted with r plus, now don't take the derivative of that first one right here, but take the derivative of the second one. And what's the derivative of a constant? Well, we know that is 0. Well, what you're going to see is that with dot products, order really doesn't matter. And you can very, very quickly even do this. You could say this is equivalent to saying 2 r dot r prime. These are really the same. You can divide by 2, and what are we seeing? R dot r prime equals 0. So this means the dot product is 0. Therefore, r of t and r prime are perpendicular. They're orthogonal. This is only if vector r has a constant length. I can't stress enough because we saw earlier how r in yellow and r prime, which is up here, just because you take a derivative of a vector does not mean that the original vector and its derivative must be perpendicular. This is a very special condition when vector r has constant length. We're going to use this idea later to help us out, to help us work out some future theorems. To wrap up, as we're finishing here, you can see if I have a vector function, if I'm going to integrate, I would just integrate each component, the x, the y, and the z, or the I part, the j part, and the k part. So let's do that real quickly for part A. My goodness, if we're going to real quickly work this thing out, the integral of r, well, tell you what, let's write r. I really like to write it, well, it is written in components. That's definitely fine. Tell you what, we can write it this way. We're going to say integrate 2 cosine of t dt. Here's the integral of sine of t, the integral of just a 2t. And what you're going to see very quickly is the antiderivative of cosine is sine. So we'll get 2 sine of t. You might say, where's your constant? Well, we'll get to that in a moment. Negative cosine of t. And then right here, if I'm integrating 2t, well, that's going to be t squared. Right now, I could say here is a constant vector, constant length and constant direction. But the way we can write it very nicely, could we have just done this? Just write like a C1, a C2, and a C3 for, individual components? Yes, definitely we could do that. There is your integral. And, I'm showing you this plus C with an arrow because it's going to show up soon enough. Guys, this last part is going to be pretty much exactly the same thing. What you're going to see is that you're just going to be integrating between 0 and pi over 2. One sec. So you're just going to integrate each of these components with the bounds from 0 to pi over 2. I'm going to leave it to you to confirm. Just if you did each of these individually, you'd wind up with this vector here. So good luck, and we'll pick up with our next video.